In question 19, we are tasked to study a sequence modulo 10. That's what's meant by taking the units digit, and the sequence in question is n times n plus 1 divided by 2. Usually, the most useful property of a sequence in modular arithmetic is its period, and here you might think that the period of the sequence on first glance is 10. Well, that's wrong, and the second guess should be 20 because you're divided by 2, and that'll be correct, as you can verify here. Taking the n plus 20th term into consideration, it leaves a remainder of n times n plus 1 divided by 2 after you simplify the expression after expansion by taking out 20n and 210. And so we have verified that the sequence modulo 10 actually has a period of 20. So our next step is to find the value of the index r 2017 to the power 2017 mod 20, and that can be done with Euler's-Torsion theorem, which states that any number coprime to 20 raised to the power of the torsion of 20 will give 1. So to calculate the value of 2017 to the power of 2017, we first replace 2017 by 17 mod 20, and then we take it to the power of 2017 minus, well, you could choose any multiple of the torsion of 20, which is 8. I'll leave this to you, and here 252 is chosen for the ease of calculation, and this gives 17 mod 20. And so now we find that AR is given by 17 times 17 plus 1 divided by 2 mod 10, which is 3 mod 10, and that's our answer. In question 20, we're tasked with approximating the 1001st term of a sequence that has been defined recursively. And the first step would be to express this recursion in a much more palatable form, dividing by an on both sides to leave an plus 1 on the left and terms involving an on the right. Now the next step, which is much harder, is to play around with this recursion. And after some time, one may find that the correct way to play with this is to square both sides. Because the error term, 1 over an squared, is actually very small, and after neglecting it, one is left with the simple recursion an plus 1 squared equals to an squared plus 2, which immediately gives an approximation for a 1000 squared as 5 squared plus 2 times 1000, which is conveniently 45 squared, such that a 1000 is around 45. And now all there is left to do is to verify that the error terms 1 over an squared do not add up to a value that would make our approximation invalid. And so we do this by bounding each error term under 1 over a0 squared, since the an's are increasing, which is 1 over 25. And so we can obtain an upper bound for a 1000 squared as 5 squared plus 2 times 1000 plus 1000 over 25. And we notice that this number is less than 46 squared, so that a 1000 lies between 45 and 46 and therefore has a floor of 45. In question 21, we are tasked with being meticulous. Firstly, since 21 is equal to 7 times 3, where 7 and 3 are coprime, the Chinese remainder theorem allows us to study the divisibility of the number by 7 and 3 separately. Starting with the divisibility by 3, this just gives us the fact that the number of 7s in our number is divisible by 3. Next, to study the divisibility of the number by 7, we first need to compute the remainders that the relevant powers of 10 give upon division by 7. Now we begin the casework, starting with the case where there are 0 7s in the number, and all 7 positions are occupied by 3s. We notice that this gives a remainder that is not 0 mod 7, therefore there is no such number. At this stage, we identify two possible simplifications that we can employ. Firstly, we notice that removing all the 7s from the number does not change its divisibility by 7, and neither does changing all the 3's to 1, since division by 3 does not affect a number's divisibility by 7. Using this, for the second case, where there are only 3 7's and therefore there are 4 3's, we notice that there is one way that we can add up the residues above to give 7. That is 1 plus 1 plus 2 plus 3. And we notice that the first two ways to get 14, given here as 6 plus 5 plus 2 plus 1, as well as 6 plus 4 plus 3 plus 1, both actually have two ways of being accomplished, since the 1 can be from 10 to the power 6 or 10 to the power 0. And thankfully the last way, 5 plus 4 plus 3 plus 2, only has one way of being accomplished. And the third case, where the number of 7's is 6 and the number of 3 is 1, we again have no solution because 1, 2, 3, 4, 5, and 6 are all not divisible by 7. In total, there are 6 7-digit numbers that satisfy the question condition. In question 22, we are unfortunately tasked with trial and error. To improve on your coloring scheme over and over until you are satisfied with its optimality. This is the suggested coloring scheme, with 120 different colors in the green squares and a single color occupying all the blank squares. Also rather non-trivial is to verify the maximality of a proposed coloring scheme, which can be done with a proof by contradiction, supposing you have at least 122 colors. Then, if we consider the number of new colors that each row introduces, which were not in the rows above it, then we observe by pigeonhole principle that at least 2 of the rows, which we call the special rows, must introduce 7 new colors. And now if we analyze the grid column by column, we notice that other than the column's intersection with these special rows, there can be at most 5 new colors, which gives us a bound on the total number of colors under 5 times 20 plus 14 plus 1, which is already less than 122. And this gives us a contradiction, giving the maximal number of colors that can be used to be 121. In question 23, we are tasked with characterization because the definition of the sequence given is not so straightforward. But upon closer consideration of the structure of the sequence, we identify some sort of a binary structure because if you remember that every positive integer can be written as the sum over a finite subset of the powers of 2, then you can see that if you replace the base by 2 instead of 3, then the nth term in the sequence, an, will simply be n because that's the nth positive integer. And what is invariant when you go back to the powers of 3 is that the order of the terms remains unchanged. That is, if the sum of a certain subset used to be in the position n, then the sum of that same subset of the powers of 3 would be in the same position. That means that the index of your term written in base 2 would give precisely the powers of 3 that you should be summing up. And in this case, what you have to do is to sum up the 7th, 6th, 4th, 3rd, and 0th powers of 3, and that gives us 3025. In question 24, we're tasked with brute force. So given the recursion, we can find A11 to be minus 2 root 3, A12 to be 2 root 3, and so the sequence is actually periodic with period 2. Therefore, we can conclude that A2017 is minus 2 root 3, which gives the answer to be 12. In question 25, we are tasked with a chase. So I encourage you to draw your own diagram as you'll have to in the contest. So the first step in this chase is to consider midpoint M of BC. For no other reason than the utility of cyclic quadrilaterals. Here, the cyclic quadrilateral is APMC, since angles APC and AMC are right. And so observing that angle PBC is equal to angle ACP by the angle condition given in the question, and noticing that this angle is equal to angle AMP, we derive the spiral similarity between triangles PAM and PCB, giving the alternative characterization of point P as the foot of the altitude from M to BD. This fact is something we can use to express the length BP in terms of BC, AM, and BM, which are all lengths that are essentially given. We can do this using Pythagoras theorem and the spiral similarity we have just found. Next, we observe the similarity DCP similar to DBC due to the angle condition angle DCP equals to angle DBC. And here we can relate the length PC to DP and DB. And finally, using the similarity that we found above, just in a different form, so there's PBM similar to PCA, we can now express PC in terms of BP, with the lengths AC and BM essentially given. And at this stage, from equations 1, 2, and 3, we actually have enough information to find the length BD. Now, we continue the computation, beginning with the calculation of cosine C, which is 11 over 15, and following up with the calculation of the lengths BM, AC, and AM, as well as BP from equation 1. Following this, substituting the value for BP into equation 3 will give PC equal to 165 over 7, which we then substitute into equation 2 to obtain the value of BD, which is 28.